Okay, let's start. Everybody's ready. So welcome to the final talk of the penultimate day of the school. So we're very happy to have Maxime Peyrard with us. So Maxime is a professor in Grenoble. He's in this group called, what is it? I forgot. LIG, which is Laboratoire d'Informatique de Grenoble, and with CNRS. Before that, he has a PhD from Darmstadt. He was for a while a postdoc at TPFL, and now he's back in Grenoble, and he's here today to talk to us about the search for foundations in AI interpretability. Thank you, Maxime.
Okay, thank you very much. Okay, thank you very much. I'm very happy to be here and to be talking to you. So we will discuss about AI interpretability, and we will discuss a bit about the search for the foundations. So I think it's a field that is very recent, and there's a lot of ideas, a lot of energy that is being put into this field of research. But I think we are a little bit in a pre-scientific stage, and I think it's worth for us considering how we could make the field into a more rigorous foundation. So that will be the discussion of today. So, but before starting, we can ask ourselves, why do we want to explain? Why do we care? So we had the panel before, and we talked about some of the applications with responsible AI deployment. So there are all these practical reasons that we care about in AI interpretability, like transparency, trust, but also accountability and legal compliance. So we want to provide explanations for other actors to use them and to do something with it. Then there is also the aspect of error diagnostics or continuous improvement. So we want to understand what are the failure points in the computations or in the behavior of the AI systems that we use so that we can improve them or continuously improve them. And then there is also the aspect of communication, education, and these things that were talked about by Lucas in his talk of when we understand better the material, so better the AI systems, we can build around them in a more clever way or exploiting better their capabilities, but we can also communicate to the general public or to experts also the limitations, the proper limitations and the proper capabilities of the systems. But I think, and that's also the angle that we'll take in this talk, that there is also a different type of reason why we might be interested in AI interpretabilities, which are about big scientific questions. So we participate as AI interpretability researchers in a bigger scientific research program, which is about explaining complex systems. So there are many complex systems, and there are entire fields of science that are dedicated to understand these other complex systems. So for example, neuroscience is busy with understanding the brain. They do kind of brain interpretability in some ways. There are also climate models that are very complex and need understanding, or immune system and a wealth of other complex systems. And all of these systems, they have something in common, is that there are information processing systems that are computing information in a very distributed fashion. There are many components that process information, and there is some emergent behavior that we can observe and measure, and that is kind of puzzling, and we want to try to understand it. But there are open questions for all of us and all these fields of science. It's like, what should be explained even? What is an explanation? What is a valid explanation, or what makes an explanation valid? Or how do we go from observations or manipulations of the system to the construction of valid explanations? So in AI, we are well positioned to contribute to this field because we are actually the simplest complex system to study. So AI are fully observable, AI systems are fully observable, fully manipulable. So we can compute all types of counterfactuals, we can observe as much as we want, we can set the system in any settings that we care about. And this has been recognized by the other fields of science, the other complex system science. They have written many position papers saying that they should try their own method, their analysis method on AI interpretability, because for them, it's a benchmark. It's like, if their methods cannot solve AI interpretability, how could they hope to solve their much bigger problems where there are partial observability, a partial ability to manipulate the system? So we are in a position where we can contribute to this bigger program of research, and we can welcome other fields of science, or maybe contribute to these other fields of science if we manage to speak the same language, and if we manage to create rigorous foundation for the field of AI interpretability. So what we will do is take a little bit of a high-level tour of ideas that we have in our field to explain the behavior of AI systems. And we will take a bit of a critical look, saying what are the problems with these different ideas and approaches that we have, taking some inspiration by some other fields of complex systems, or in particular neuroscience, because they've been thinking about it for quite a while, and they encountered many of the problems that we are encountering. So they might have some ideas for us. So maybe the first and most obvious idea is to just look at the behavior of the system. So imagine you have an AI system, you can feed it some input and see what output it's producing. And we can carefully craft the inputs however we want. We can measure whatever happens in the output, come up with hypothesis, high-level explanation of why, what is going on in the behavior. And this is just the general idea of we look at the input and the output and we come up with ideas. And maybe one of the zeros idea of behavioral testing is benchmarking. So benchmarking is actually, we just chose a set of input, we feed it into some AI system. This system produces some output, and we measure some property of this output, like one number. This one number, like average accuracy or something, is a one number summary of some aspect of the behavior of the system that we decide we care about. It's a very dense summary that condenses a lot of information, but we might find it useful in some ways. Maybe more in line with what we have in mind when we try to understand the behavior of the system is we can carefully manipulate the inputs. And by carefully choosing transformations of the inputs and measure what is the effect on the output, we can maybe slowly construct an understanding of what things in the input cause some effects in the output. So this was already an idea that was recognized several years ago in the field of NLP, with this idea of counterfactual examples and the boundary decisions and the contrast sets. So the idea was to look for inputs that have high impact on the effect on the output, or high effect. And in this way, we can slowly construct an understanding of what is going on with the behavior of models. So here's actually an example of the opposite, when we make some modifications of the input that we expect should have no impact or no effect on the output, but they actually do. So these are examples where we put prompt, asking a question to some LLM, and the LLM can answer the question, but if we modify the prompt in ways that should not modify the reasoning or the answer, we observe that sometimes it actually does. So this is a bit puzzling, and points to the fact that there are some behavior in the computation that we don't understand. So it's a foreshadowing that maybe we should look inside the computation at some point. And maybe this idea of looking at control changes of the input and how they affect the output has been taken to the more rigorous setting of feature attribution. So in the field of feature attribution, there was a very active field of research a few years ago, where what we're trying to do is we look not just at manipulating the input, but we manipulate the mathematical representation of the input that is relevant for the AI system, which are the features. And there are many methods that try to just look within the feature what matters to have the prediction or the behavior that we observe at the output. So there are many methods that do that, and they typically produce this kind of explanations for some predictions in the terms of saliency map. They show you in images, for example, what was relevant to the prediction that was observed. But we come to see the first of many issues that we will discuss today. There was this work a few years ago where they looked at testing the saliency map, so the feature attribution techniques, on randomized neural network. So you take a neural network, you look at the saliency map that it produces for some explanation. And then you do the exact same thing when you randomize some layers or many layers of the model. And it turns out that the saliency maps were very similar in the random network and in the trained network. So this is a sign that something is going wrong if we can find explanations even when there is actually no behavior that we know. This is also an opportunity for us to do a first detour in neuroscience. So in neuroscience, they also have the same problem as we said. And for them, they came up very early with the observation that behavior is not enough. Behavior is not enough, and we have to look at the computation, because within the computation, we can find some objective, measurable, and generalizable predictors of some aspects that we care about in the behavior. And this dates back already to the 70s, and even the David Marr's levels of analysis. There was already the 3 levels of analysis that we need to understand if we want to understand behavior. So this idea is very obvious, and for them, it's very obvious for us. It was not at the time, but this started a whole field of brain imaging and so on. So they have to cite all this paper whenever they have to ask for a lot of money to get fMRI equipment in their lab and then fMRI studies. But so for us, we have the same conclusion. It's like behavior is not enough. It's very easy to come up with a high-level explanation by just looking at input and output. But is this explanation consistent with the computation or the low-level implementation that we know is happening? So then we know what we have to do. We have to look at the computation. So then we do open the black box, and this is a deep learning architecture, surprisingly. And this architecture is computing information via some neurons or some components that take some real values. For each input, this different component takes some values, and we can just record them and store them in some vectors because we like to have vectors. And then we can simply study the patterns within these activations. So we study patterns within the computation of the AI model. So this is a very general idea. There are many ways to do it. I will give you a very fairly old example of something we did when I was at the end of my PhD and beginning of my postdoc. So we were collecting these types of data that were from The Onion. So this The Onion is the satirical news. They write a satirical news headline and news article, and we're asking humans to modify this satirical headline to convert it into serious or non-satirical headline by doing the minimal amount of modification. So we could keep track of which tokens were modified and not modified and so on. And then we can easily feed these kinds of input or paired input into some LLMs. So at the time, it was not very big models. They were BERT and GPT-2. And you can compare the computation because between 2 pairs of the same sentence, but one is satirical and the other one is serious, and you can compare the computation that is happening. So you can study the patterns. Something interesting that we saw is that there was one head that attended a lot to the part of the satirical news that the human decide to modify in order to make it serious. So this finding is interesting, but it's also validated by further manipulation. But this is also foreshadowing for what's coming next. So this was just a fun finding. But another idea that I like a lot is the idea from this paper where they were comparing not just patterns of activation between different inputs, but for the same input, patterns of activation between different layers. And so we can compute the similarities between the activation computed at one layer versus another layer for the same input. And in this work, they did it with canonical correlation analysis, but there are many ways to compute the similarities. And the results that they had were quite interesting. So they trained some computer vision models on the Cypher-10 benchmark. And the more you go to the right, the more the model is trained. So at the beginning on the left, it's randomly initialized. And each plot is a pairwise similarity matrix. So it tells us the similarity between 2 layers. And we can see that the more we train, the more there are like these pairs of layers or triplets of layers that start to compute exactly the same thing. So they are redundant. And maybe there's some theory that says that it's actually beneficial for learning, but once it's learned, the model can be easily pruned and by removing these redundant layers. And that was an idea that was actually used fairly recently to prune a lot of the llama models by doing more or less this similar more or less this exact idea. But maybe to take the idea further of studying patterns of activations, there's the idea of probing. So probing is a very general tool that we can use. So we collect the activations for a set of inputs that we care about. And there is something that we want to predict that we care about. We can say a label, for example. And we simply train some machine learning model to predict the thing that we care about. So like some aspect of the behavior, for example, from the input feature that are the activations. So the features are the activation, the state that the computation has taken during the forward pass. So implicitly, it means that because this is a machine learning thing, we want to have some train and test, and we want the prediction to generalize on the test set. So we have this whole machine learning pipeline that is going on. The assumption is that if we can predict robustly, like meaning generalizing on the test set from such a machine learning approach, then the information about the label has to be encoded somewhere in the features, so in the activation. So it means inside the computation or the part of the computation that we are looking at. So this is the idea. If we cannot predict, then it means that the information is not encoded. And maybe one of the early example of this idea was sort of 5 years ago already at ACL. So in this case, we can take a sentence encoder. So it means we take the entirety of the sequence, we represent it with some vector, and we use this vector as the input to some classifier for some task that we care about. In this case, relation classification. So we try to classify some entities, so the relation between some entities in the input. And once this is trained end-to-end, we fix the model, and then we want to do an interpretability question about it. So we can train a probing classifier simply by taking this vector that represents the sentence and putting on top of it a classifier to predict completely something else. In this case was linguistic features. And if we can predict the linguistic features, which in this paper they show it's the case, then if we can do it, it means, or we conclude, that the sentence encoder somehow has used or learned to keep the linguistic information in order to do the other task. And so that was an interesting finding that also started a lot of the probing work. So there are many, many examples of probing, and maybe I will put them in the extended version of the slide, but in order to go faster at the high level, I will directly go with the problems we might have with probing. So probing is a machine learning task. So it's a machine learning tool. So especially the input of the input dimensionality is very high, and we try to predict something with very few input usually. So it's very easy to find signal within the noise. There are a lot of theoretical arguments about how we should be very careful in how we choose our probes, how we train our probes. And actually, this is the time for our second detour in neuroscience. So neuroscience, they were spending a lot of money building fMRI EEG machine to record brain activations. And what were they doing with these brain activations? They were computing, of course, some kind of probing. So they were not calling it probing. They were calling it multivariate pattern analysis because it sounds fancy, or brain signatures because it sounds cool. And so they were doing a lot of this thing. And here I put some article that's kind of a review of these ideas. And then enters one of these experiments that is quite interesting and funny, is the dead salmon experiment. Maybe some of you have heard about it. So there was some dedicated neuroscientist that was not afraid to waste some fMRI time that decided to put a dead salmon inside a fMRI and make this salmon pass a standard experiment that was given to humans. So they're showing to the dead salmon images of humans that were sad or images of humans that were happy, and recording the brain of the salmon, the dead salmon, while doing so. And then you pre-process the data, you do all your analysis using the standard tool of neuroscience at the time, and you found for sure that there is some part of the brain that is highly predictive of human sadness or human happiness. So, and in the interviews, the writer said, yet the salmon was dead. So there was, this is actually a funny thing, but it started also quite a bit of a discussion on the methodology of in neuroscience. And so there were two answers to this problem. One is a purely methodological one, that you realize that you're actually doing a statistical inference. And if you take it seriously that you're doing statistical inference, it's not enough to just generalize well on the test set. You have to take into account the base probability that this kind of thing might happen. And you have to take into account how you measure uncertainty. So in this case, there was like multiple comparisons that happen naturally because you try out so many things implicitly. So they could correct it by simply doing uncertainty estimation correctly. But there was also a more conceptual, fundamental discussion about the fact, even if there was this correlation, then there is no guarantee it would not have meant that this pattern of activation actually causes the behavior. And this would have been a good example. There is no behavior. The salmon is dead. So there's a causal statement. We cannot just make a causal statement because there is an association between some brain patterns and some behavior, something that we observe, that we care about in the external, outside world. So you have had the lecture this morning, so you know that, yeah, there's a question.
Yeah, so I have the microphone, but my curiosity was about the dead salmon. That means that it has some activation. How does a dead salmon or a dead anything has some activations for the fMRI?
Yeah, that's a good question, because there's some just variability in the measurement process. So for them, when they just put the anything inside the fMRI, there is some variability.
Yeah, but why does it happen particularly in the brain?
I think it might happen anywhere, but it happens in the brain because this interacts with the tissue that is in the salmon. So it could have happened, like it happened. It's a nice story because it happened just at the edge of the brain. It was barely almost on the bones and so on. So it's if it had been on the bones, it would have been less of a fun story. But it's
like several salmons.
Yes, they had to spend 20 salmons to find the good one. So yeah, so basically we know the conclusion is fairly straightforward because you had the lecture this morning, and so you know that correlation or associations, they're everywhere and they're easy to find, but they don't necessarily generalize. So we can formalize this idea that predicting is not understanding for any type of machine learning based interpretability. Every time we optimize and we try to find some patterns, we have this risk. And actually, if you think about it, the first feature attribution problem where we could find meaningful saliency map on random neural network is already a kind of a dead salmon type of experiment or type of finding that we had. And for the probing, there is also another dead salmon type of finding more recently, where the sparse autoencoder are kind of a unsupervised probe. And in these people, they went and tried to find explanation in a random neural network using sparse autoencoders. And they could find plausible explanation in a randomly initialized neural network, which is also a case of dead salmon type of finding in our field. It doesn't mean that all the findings are bad. It just means that we have failure cases that indeed point us towards a need to think our foundations more seriously. So, okay, correlations are not enough, so we have to do causation. So this is the next step. Instead of looking for neural correlate, we look for causal patterns. And actually, causality is very central to the idea, the concept of explainability. Like philosophers of science very consensually agree that explanations must be causal. And this is because of a very profound, very simple, but profound idea that causes explain their effects. So this is an axiomatic statement. And then we say that when we want to have understanding is because we want to be able to predict what's going to happen in many different scenarios, so under many different types of interventions from the external world. But also when we are the ability to control, so it means if we can apply some external modifications to ensure some behavior, then when all of this is there, we have the sense that we are understanding the system. So causality is very important. And then we have one of the most basic way of introducing causality is to introduce some interventions. So we can now go inside the computation and modify it and see what happens. So one of the basic ideas is the so-called amnesic probing. And in amnesic probing is we do probing first, but we don't just trust the result of the probe. We will do further interventions to validate the probe. So in the case of amnesic probing, the idea is simple, is we want to take the activations that the probe uses to make its prediction, and we want to modify the values of these activations such that the probe doesn't work anymore. So this is kind of a knock-off experiment. We want to remove the ability of the probe to be able to do its prediction. And then we look, is this intervention on the computation also removes the behavior that we care about? And if that's the case, then we have better reasons to think that whatever the probe is seeing is actually causally linked with the behavior that we care about. So this is a very routine type of check, like Lucas was talking about it in his talk, and like many of us do when we do probing, we just do first probing and then we do further validation by doing some interventions. But the idea can be generalized quite a bit. And the central main idea of using interventions rests around the concept of causal mediation analysis. So just to explain briefly what causal mediation analysis tries to do. Imagine we have our model. This time is an LLM. It's taking some tokens in and it produces some next token distribution. So we look at the computation and we might ask what is the effect of this specific component on this specific output that we see. And this is exactly the scenario, the setup for causal mediation analysis, which is a very well-established domain of study in any field of applied causality. So in this scenario of causal mediation analysis, we have this type of causal graph where X causes Y. There is no question about it. X causes Y. The input causes the output. But the question is, by which path of influence does X transport its effect on Y? Is it via some path that goes through some mediator, we call some variable that we care about, M, or is it via all the other paths? So in the case of the transformer, it's very clear, is it all the paths that go through this component that are responsible for the effect, or is it all the other paths, computational paths? And causal mediation analysis gives us the exact types of interventions that we need to do and the exact type of counterfactual that we need to compute in order to be able to extract and disentangle these different paths of influences. So in standard medicine, for example, is extremely hard to do because we cannot compute this counterfactual. So we have to make assumptions and approximations and so on. But in our case, we can actually compute exactly the counterfactual and we can compute exactly the causal mediation analysis formula. It takes a bit of time, but we can do it. So one of the earlier examples of using causal mediation analysis for interpretability was the case of gender bias. So in this work, we have prompts that have a next token completion that could be stereotypical. And the point is to apply causal mediation analysis to try and find, is there some component inside the neural network that is responsible for this gendered prediction or this gendered bias? So without going into the details of how causal mediation analysis works, you can compute the various state of, you can record the state of the model when it's looking at this prompt and when it's looking at slightly modified prompt that changes the prediction. So for example, if you change the word nurse for man in this prompt, then the model will not output she as the next token, but will output he. And by looking at the states in these two forward paths and exchanging the values of the states according to the causal mediation analysis formula, you can compute the effect of the component on the output. And then you can repeat it for each component in your model. It takes a while, but you can do it. And in this case, so it was Peyrard model again, you can see that there are few attention heads that are very causally linked with the gender prediction. And this, so it's not like probing because it's directly causally linked to the prediction. So you know that by changing the values artificially from the exterior, of these attention heads, you would modify the behavior. You would modify from she to he and so on. So this is interesting. It was used quite a bit and became a quite central idea. Another example I think is interesting is the one about factual recall. So this time you take more modern LLMs and they have learned to answer a lot of factual queries. They have parametric knowledge and they can answer many queries. So you give them these queries and you can compute again the causal mediation analysis formula saying what components are responsible, causally responsible for predicting the correct answer to a factual query. In this way, you hope to be able to have some insights about how the models are retrieving or using factual knowledge in their parameters. So in this work, this is exactly what they do. What they did, they just apply a causal mediation analysis on some GPT models. And you can see that there is a high causal effect on early MLPs in the model. Then this the setup was expanded, the way to compute the causal mediation analysis was improved, but little by little, we could come up with this understanding of how factual knowledge is likely to work. So we think that now facts are localized in a few MLPs in the early layers, and these MLPs act as associative memories to store the factual knowledge. And these associative memories are activated by some trigger sequences in the prompt. So this is an interesting story, or we're building up across several papers and a stream of paper that of some kind of an understanding. But then we can again go one more step forward and try to not just understand one component at a time, what's the impact of one component, but we can aim to understand more globally what's the impact of what's the entire algorithm that is being computed by the model when it's doing some kind of behavior. So this is the end goal of mechanistic interpretability. Here it said to reverse engineer the trained neural network in order to find the algorithms that are embedded in the computation. And in the word embedded, what is meant is that they are causally there, so causally aligned, causally present. So typically, one of the main approach inside mechanistic interpretability is to apply a lot of variants of the causal mediation analysis to find circuits which are not just one component responsible for the behavior, but an entire subset of the computational graph that is responsible for the behavior that we observe. And then once we have this circuit, we can try to interpret its component to have an understanding of what is the algorithm that is happening. One of the success story of this idea came from the computer vision, where people could say, actually, these components, they are edge detectors, these components, they are texture detector, and then this other component combines these two to become a face detector and so on. And so we had this intuition that it was kind of a circuit, and the circuit connected some kind of components that were computing something of interest, and then we build up our understanding of what is the model doing. So that inspires now for the field of LLM and for AI in general. So we might think this is the end of the road, like we have found something that is solid and that is useful. And it's just a matter of perfectioning the way we evaluate, the way we compute, and so on. But it turns out that it's not exactly the end of the road. And it's the last detour that we'll do to neuroscience. So in neuroscience, they were looking at the behavior, spending a lot of time in the fMRI machine. And then they say, actually, it's not enough to just do the probing or the multivariate pattern analysis. We have to take into account causal phenomena. So for them, it's very difficult to come across causal phenomena. So you spend a lot of budget to justify doing neural stimulation or waiting for patients to have lesions and hoping that you get some causal insights because there are some naturally occurring interventions. And then you perform your causal inference. It's very hard, but little by little, you think maybe if we amass enough data like that and we do our analysis correctly, we'll end up with an understanding of the brain, a mechanistic understanding of the brain. But then they started to ask themselves this question, like, how do we know actually that our explanations are correct? How can we trust our analysis method if we never see an example of a brain, a computation or brain, and some true ground truth explanation? How can we know that the analysis is actually correct? And then there is this very amazing paper, I think, because it's a very good idea, saying, could a neuroscientist understand a microprocessor? And they said, okay, let's take a naturally occurring example of a complex system, fairly complex, for which we know actually the explanation. So it's not a brain, it's very different than a brain, but at least we can treat it as if it was a brain. We say the transistors are a bit like neuron. And for sure, our analysis method and our analysis toolkit, there is nothing brain specific to it. It's data science. They should be able to pass this test. They should be able to understand the microprocessor, because we are in the state where it's much easier than the brain. Now we have perfect observability, perfect ability to manipulate all the transistors that we want. So we can do all our analysis methods in the best possible scenario, and we surely will be able to understand the microprocessor. I mean, of course, they did this because they had the suspicion that they would not be able to answer, but the answer was actually no. Nothing meaningful came out from the analysis toolkit of the neuroscience. And I think particularly interesting for us is the fact that even a very extensive intervention study gives no useful information. So you get some idea that this transistor in this context has a high impact on the output. And so what? Saying, do you get the idea of a memory, of buses, of arithmetic logic units and this kind of thing? Do you get persistent state and so on? No, nothing like that emerges. So maybe we are the problem that we might be also in the same situation. I think if I was neuroscientist when I saw this paper, I would dedicate my time to understand the microprocessor. But even though we are not neuroscientists, we could also try to understand the microprocessor. And I think this is what we wanted to do with a PhD student when he started in my lab. So we had the idea to, let's try to understand the microprocessor. For sure, mechanistic interpretability, we can do something. And the problem is that we quickly understand by looking at the methods that they would never work. Even the more modern method that we use now, we cannot understand the microprocessor. So we downscale the problem. So let's try to understand the ALU, just an arithmetic logic unit. And then let's try to understand the XOR. And this is a hard system. So we found some problems. There is some problem, and it's the same theme as the other problem that we found before. Basically, even if we take very simple simplification of the microprocessor, we can find almost any explanation, causal explanation that we want if we look hard enough. The problem is that the criteria that we use currently in mechanistic interpretability are not strict enough. Even though they are causal and we do a lot of counterfactual to test them, they're still not strict enough. We can way too easily find any explanation that we want, even in randomly initialized neural networks. So this is another dead salmon type of problem. Maybe to give a little bit of details about this experiment is that, broadly speaking, mechanistic interpretability, now there are many methods that have been developed. They can be categorized in two groups. The one that do a lot of causal mediation analysis to extract the circuit. And once the circuit is there, try to interpret its components, so doing some type of grounding. So this is the standard path. But there is also another path that I think is very promising, but up until now fails, is you start with a candidate algorithm. You postulate a candidate algorithm. And then you try to look, is this algorithm causally implemented, like all this state and all its variables causally aligned with some of the states and variable inside the neural network. So you try to look if it is there, where it is. And if you cannot find it, you say it's not there. And so we do a very toy exercise. So this is only an illustration from the paper, but I think it's enough to convey the idea. We take a super tiny model that is trained on XOR, predict XOR, so it's super simple. And what would be a toy exercise in interpretability? I think ideally this kind of thing would be the thing we would give to master student when mechanistic interpretability is more mature and say, interpret this in 1 or 2 hours, you apply the tools and you find the interpretation. What could be the answer? The answer could be, what is the sequence of logic gate that is implemented? Is it that these two neurons are a bit like an AND gate, and this one is a bit like an OR gate? Or is it that there is nothing like that? It's just completely distributed and there is nothing sparse and nothing that we can extract? Or or if it's a sequence of gates, where is it implemented and so on. So this could be the questions we might ask. And in this case, it's small enough that we can actually enumerate all possible solutions in reasonable amount of time and test them. And we can test them with the criteria that mechanistic interpretability set for itself. So there are many criteria depending on the algorithm that you use. And we say, this is a valid explanation and I'm optimizing for it. Or someone else will come and this is a valid explanation, I'm optimizing for that and so on. So we can test all of these criteria and see how many explanations are valid according to these criteria. And on average, for just this example, we could find 85 unique circuits that have perfect accuracy. And you can see that the union of all these circuits contains the entirety of the computational graph. And on average, for each circuit, you can find 25 grounding explanations. And this is not even counting the fact that an AND gate or an NAND gate are basically the same thing because you just switch your interpretation. These are not counted there. So this is a lot, and there's not just few explanations, and we have to choose based on some regularization. Is a lot. Almost all of them can be found. In the same way, in the other type of approaches, the one that look at algorithm first, for every algorithm that we try, we could find on average 159 159 locations where they are implemented. And this is on average for many algorithms that we try, candidate algorithms that we try, so we cannot distinguish. And we chose the algorithm to be meaningfully very different, the one from the others. And I don't go into more details, but this is robust to if you change many parameters of the scenario. So if you make the model larger, if you overtrain, undertrain, do it multitask learning, make it predicting several other things in parallel. So if you change the complexity of the task with respect to the capacity of the model or this kind of thing, it doesn't really change the conclusion. So we have a general theme that is emerging, is when we were looking at the behavior, we had the problem that there are many explanations compatible with the behavior, but we don't know which one matches the computation. So which one generalizes. And then we went to look at the computation, and when we were looking more at correlational analysis, we had many causal mechanisms that are compatible with the observed patterns of association. And the question is which one generalizes then? And we thought we would be safer in the world of causality and causal mediation analysis, that is the world in which things generalize, and this is the world that we like, actually, I think most of us. But it turns out that there are many causally aligned explanations, and so it's not clear which one generalizes. So this is the theme of like identifiability issues. By identifiability, I mean the fact that there are too many possible explanations. And this lack of identifiability is not just a little thing that we can fix. It leads to generalization issues. So it points to the fact that we would need stronger, more robust definitions and foundations on which we base our methodologies. It doesn't mean that the findings that have been occurring with this type of method are wrong. It's just that we can find easily counterexample that shows that the foundations are not so secure. Right? So maybe to finish in the last few minutes, I want to give maybe some ideas of what I think we can do. And in the same way, here, if you think about it, it's dead salmons everywhere, like type of problems that we have. And in the dead salmon, there was two ideas to fix it. One was methodological, by thinking about statistical inference, and the other one was conceptual. And I think we have also a similar story here. One is purely methodological. I think we can give up a bit the hope to find the truth, the explanation that is there lying inside the neural network, just waiting for us to find the genius experiment that will reveal itself. And we could move to a more instrumentalist perspective and say, actually, what we are doing is an exercise in statistical inference. So we have to accept and recognize that even if we don't say it explicitly, it is there. There is a distribution over the data that we have, which is computational data, computational traces, but there is a distribution on it. It comes from the input data that we choose and the generalization scope that we aim to achieve. So there is a distribution, there is probability distribution, and we make some assumptions about it, whether we consciously know or not. And then there's something that we want to measure, like maybe we want to find maybe the algorithm that is embedded, or some mathematical structure that we care about. And this in the language of statistical inferences, the estimate, the thing that we want to estimate is a property of the distribution. And once we have defined that, we can actually start to do estimators, so the things that go from the data to produce an estimate of the thing that we care about. But then once we do this explicitly, it becomes very clear the type of questions we have to answer. So for example, we have to think about the identifiability. Now there is a statistical model. Can we even infer this property that we want or not? Because on most of the previous approaches, we were talking about lack of identifiability, but they are not framed as statistical inference problems. So it's not even well-defined, the notion of identifiability. But if we do explicitly the task of saying, here's the distribution, the assumption I make about the distribution, and here's what I want to measure, the assumption that I make about what I want to measure, then we might have identifiability questions, theoretical and not just empirical. And maybe identifiability might not be such a big of an issue. We deal with non-identifiable problem all the time. It's just we need to find proper regularization or proper equivalence class, but we need to engage with the question. And then for the estimator, there are properties of the estimator that we might care about. Like, is it biased? What is its variance? Is it consistent? So like if I collect more data, do I get to the correct answer? Yes or no? And maybe the most important is the distributional property. Like if does my estimator generalizes? So if I change properties of the distribution, will it still work? And again, the uncertainty quantification, that depends on the assumption that we make about the distribution. So these kind of things would already fix most of the dead salmon type of problem. But I think the bar is very low. We don't want to just not find something in random network. We want to find meaningful thing in trained network. So maybe the more conceptual change that we can do is what we call computational summarization, or this similar to causal abstraction. And if you think about the problem with the microprocessor, you could do any type of intervention that you want. You will never come back and say this transistor is the memory transistor, because there is no such thing as a memory transistor. Memory is emergent behavior that comes from the coarse graining of many transistors. So if we want to be able to capture these kinds of phenomena, we need to be able to model them. So there is a field of causality that deals with this idea. It's called causal abstraction. Causal abstraction provides a way to tell us when a causal model is actually an abstraction of another one. It is actually when this higher level model, the variable in the higher level model, are coarse graining of the variables in the low level model, and when the counterfactuals are preserved. So like the behavior of the high level variable matches the behavior of the low level model under all possible interventions. So there are various ways to define what we mean by matching and the counterfactual are preserved. This is very theoretical. Actually, Adele works on this topic as well, so you can also talk to her about it. It's a very active field of research. But for us in interpretability, we could recognize that our neural network is a computational, is a causal model, is a computational graph, and we can search for the explanation as being a small causal model, a small computational algorithm, if you want. So I think I like the idea of computational summarization, because it shows us that what we start with a computational model, and what we want is another computational model that just is much simpler, much smaller, and that preserves the most important aspect of the computation. And also it makes it clear that depending on the question that we ask, what is important might change. And in the same as in text summarization, we might have different summaries depending on what we care about. So I think this is the idea that we need to take into account. We actually have now recent result in my lab that if you start to make some explanation validity metric with this idea, you can actually find that the microprocessor is the one and unique explanation of the analog circuit. So it doesn't tell us how to find it, but at least it tells us that if we were to enumerate all possible explanations and test them all, then we would find the good one. And so that's a little step towards this goal. But I think I want more to encourage people that work in this field to think about the foundations. There are like a lot of work to be done in the statistical inference aspect. There's a lot of work to be done in the computational summarization aspect, and is very much open to a lot of contributions to how we can formalize this field a bit more. And maybe hopefully we can all meet in a few years and say that we finally understand the microprocessor. That's it for me.
Good. We have time for questions. Yeah.
Thank you very much. I think this is very exciting directions. I have maybe one more broad questions about the why identifiability is so important. I think one way to think about it is that we will find often multiple valid stories. For instance, in physics, we have two valid stories of reality, and we struggle to find which one is true in the limits, but there are ways to say this one is not valid in this context and this other one is not valid in that other context, but both are valid. So how could we go and maybe have methods that will be able to say, well, we have two or three or a small distribution of possible stories, but they are there are this context or that context that they are not valid, something on that line. And the other one is how do you think about this aspect of memory, amortization on when you build these hierarchical summarizations? Because it seems to me that every computation can be amortized or saved as a memory, or every computational trace is a memory of an algorithm that's running. But how do we build it on top of each other? Like if you have some ideas of it. Yeah.
Yeah, so very good question about the parallel with physics. So there are two things to say. One is it's not a problem of identifiability, the fact that we have many valid stories, because the stories might be at different levels of abstraction. They might take a different angle, postulate different basic entities. So identifiability is more when you fix the rules of the game and you say, this is the entities that I use for explanation. This is the criteria for validity. This is my level of abstraction. Then you kind of expect to have one. So it's a good, maybe we don't need identifiability, but we need to engage with the question. And we need to know what's the equivalence classes, at least, of things that are unidentifiable, or the level of non-identifiability, and does it matter or not? In this case, the example that we have, they are just so broad, like almost all explanations. So then how can you choose? You know, it's not some explanation up to some amount of permutation or some amount of. So this is a bigger problem. Also, the difficulty with non-identifiability is a problem of generalization. So because you have many explanations, some of them in some undone experiment and undone modification will not generalize well. So I think that's why you also need to bring the statistical inference perspective to have your uncertainty that is measured. There are these philosophical questions about scientific realism versus the instrumentalism, and the underspecification even of the universe, like maybe in the philosophy of science, maybe the universe is non-identifiable, and it could be just a finding. It could be a finding that AI systems are just not identifiable, and maybe at some point it might be a theorem that we cannot have identifiability and this and this and this, the 5 other properties that we would really want to have, or something like that. It could be, but it's open for a question. And the second thing is about the temporal aspect and the fact of taking into account memory and building this. So this is also quite a bit missing in the practical approaches. Usually we only look at one token. And so, but actually there's a sequence of tokens that are being predicted. Methods tend to lack ability to deal with this. The framework of causal abstraction also has related cousins idea, like causal emergence, that are supposed to have abstraction both spatial and temporal, but is very far from being actually used in practice. So.
Okay, thank you very much for the talk. So I have 2 questions. The first one is about circuit discovery. Can we really say that this circuit is responsible for a specific task? Because what's usually done, like in the interpretability in the white paper, they basically found a circuit that is responsible for the indirect object identification task by deactivating the rest of the neuron of the network, and basically they found that the model still works for the task. But what they actually found is that even when they activating this circuit, the model still does the task. So is this, can we really conclude about this? And the second question is, what's your opinion about sparse autoencoders? Because at some time there was a big hype about these models. People started to say that we'll be able to interpret transformers and identify features, and that it's a great solution for probing as we don't need annotation. But now they started to realize that they are not as good as they thought, and also that they are very costly to train. So I was wondering, what do you think about this?
Yes, thank you for the question. I think you gave two examples also that could be included in the talk. So the interpretability in the wild is actually a good example of also problems with circuits. So I agree with you. I don't think we can easily say this circuit is responsible for this behavior. And the interpretability in the wild is one of the reasons why it's a problem of generalization. So when they were modifying a little bit the input distribution, the circuit changes. And if you introduce some other interventions, then the circuit the circuit validity is not preserved. So this is also another example of this problem. It's the same for sparse autoencoder. I even included this article that you mentioned that was a bit criticizing, saying that it doesn't mean that nothing that comes out of sparse autoencoder or circuit is that everything is useless. It just means that the fact that we can find counterexample and like very striking counterexample when we can interpret a random network is a sign that something is wrong with the specification of the parameter, what we define to be a valid explanation. So I think sparse autoencoder are not there well specified enough. And you could take them and try to convert them into valid statistical inference procedure. You would have to have a lot of uncertainty estimate. I think it's not trivial to do, but you could imagine, and maybe a lot of the findings just disappear under the very high variance that you would get.
Thank you.
Hey, so something that I was thinking is like when you train like just imagine like I'm training like an LLM to do multiplication, right? And sometimes what you see is like suddenly your accuracy goes up like a lot. So here, like when we analyze the things, it's like I'm taking like a snapshot and I look what's inside my snapshot. But what if I looked at, I had my model before it had this sudden like, like spike in accuracy. What changed here? Broken.
Yeah. So I think in general, it's a good actually it's even a good idea to have better understanding, to look at the evolution during training. It's just that for now, even when we take a snapshot, it's already computationally a bit intensive to do all these causal counterfactual thing. You would need to repeat it across the temporal dimension of training to be able to have a solid understanding. So there were a few studies that used a bit circuit analysis, and looking at the evolution during training. I just think it would be a nice thing to do, but for now we kind of we don't have yet a methodology that is secure enough that we can say it's worth for us spend on a big model a lot of compute to try and get a valid interpretation across the training, like a different snapshot. But yeah.
Questions? No, it's okay. So yes, excellent talk. Thank you. David Deutsch, the physicist, he has this idea that it talks about good explanations, which are not just any explanations. And he characterizes good explanations and being those that are hard to vary. So they are in some sort of local minimum of explanation, whatever that means. So do you think that these causal abstractions are some sort of way of finding good explanations, whatever good means?
Very good question. It's actually the way we are currently justifying that we have found a good evaluation metric. So this is not published yet, but it's precisely by doing small perturbation around the explanation and seeing that the value of the validity is dropping very quickly. So this is actually very much completely using this idea.
Hello, thank you for your talk. So I have a probably a little bit vague question. So I am doing machine learning for certain applications. So often my supervisor will question me like, okay, you're interested in interpretability research, and there is pretty a lot of interesting papers of finding relevant causal neurons, layers, or circuits in a model that's corresponding to a target or a label. And he will always asking me, okay, what is it useful? Why is it useful? What is your next step? Because like we are like an application group. So I find it's very hard to answer that question. I was wondering if you could give a better answer.
No, it's a good, difficult question. Also, this neuroscientist that were doing the CUDA neuroscientist understand the microprocessor, the authors, they often like to trick their other neuroscientists and say, give me an explanation of whatever behavior, but don't use any information about where it's located in the brain. Because they say, what, it's located here, and so what? So this is also a similar question, like we have been looking a lot for where it's located. And it's not clear that it's useful. It's useful for us because we have access to, we can easily access to control. So for example, if you observe some gender bias and you know, you could do several things. You could do post-training and try to balance the distribution, or you can change your training data. I hope it would be better. Or you could do many things. One of the things that you can do that is very, very cheap is if you found the few neurons or the few places that you know will give you the desired behavior, if you consistently apply some intervention, then it might be very cheap and very easy to fix the behavior. So this is one thing. The other thing is we want to understand what type of algorithm the models are implementing so that we can predict how they will react in unforeseen scenarios. So if we realize that, for example, the multiplication was a good example, you can understand how the model is actually doing the multiplication, and you can understand just by understanding the algorithm that it's computing that it will not generalize to some scenario. So in the case of multiplication, it's easy to test, but for more complex scenario or more complex behavior, maybe we don't even think about testing all the possible scenario that we care about. So if we have this understanding, we can much more easily predict what might happen.
Yeah, thank you so much. If I may, I will ask another question, if that's okay. So I was wondering, when I was looking at the interpretability papers, there will be a lot of interpretability methods and then evaluation of those methods. So I was wondering if you can give some questions on how to make a solid paper usually when you try to make develop probably a new interpretability method or explainability method?
Yeah, that's a good question. So I think the easy fix for many of things is to embrace a bit more the statistical inference aspect. So these are very simple things that we learn to do during our part of our training. It's just that we fail to recognize that this is, despite a complex distribution and despite a complex thing that we estimate, it is actually a statistical inference estimation procedure. So we need to take into account uncertainty, and the uncertainty should depend about what assumptions we make on the distribution and what's the generalization scope. So I think we should be very careful in how we report our uncertainty. I think many of the findings that we found that could be errors, they disappear if we put proper confidence intervals. So I think it's the easiest way to get good rigorous output without working on the methodology if you work on the application. Like if you work on methodology, you can try to think about definitions and so on. But, yeah.
Okay, maybe one last question here, hopefully a short one.
Thank you very much for the presentation. I was wondering, it might be less of a problem now, but for a very long time, we had a big problem, especially in computer vision with the brittleness of models. So like the slightest adversarial attack would completely break the model. Could this be related to if we can explain a model or not? Like if the generalization capabilities of the model linked to our capability to explain how the model works?
Yeah, yes, that's a good point. So actually, the adversarial examples, they're more pointing us towards the fact that it's hard to produce an explanation that is simple, because it would mean that actually it's extremely distributed, they're extremely brittle. So it's more of a warning for us that whenever we try to look for a very sparse or very simple explanation, we might actually have the problem of identifiability. So it's more a warning. But I'm not too aware about recent development, recent work on related adversarial problems with the more modern kinetic interpretability. Maybe there are, but I just don't know.
Okay, let's thank our speaker again.